Let's have a look at a very interesting question. This is a small question from the USNCO National Exam, Part 2, question number 2. So basically, we try to make buffers with different pH by mixing the phosphoric acid with solid sodium hydroxide. So the first part is very straightforward. Just the direct application of the Hansen-Hashbach equation, right? Now suppose the phosphoric acid is H3P. So we'll have H3P to H2P minus. This is corresponding to Ka1 to HP2 minus. This is corresponding to, to HP2 minus. This is corresponding to Ka2, and finally to P3 minus. This is corresponding to Ka3. So pH 6.5 is very close to the pKa2. So we will say, okay, the major species in the buffer are the H2P minus and HP2 minus. And then we can use the Hansen-Hashbach equation, pH equals to pKa plus log the molarity of the salts or the conjugate base over the acid. So it will be the molarity of HP2 minus over H2P minus, right? So if you put the values in, this equals to some, and then we should get the ratio of these two. Right? I will skip the calculation part. You guys can try it by yourself. But actually, when we apply the Hansen-Hashbach equation, we need to realize, we directly put the initial concentration of the conjugate base and the acid into the equation. But actually, based on the definition, they are supposed to be the equilibrium concentration. So how we can say the initial concentration of the conjugate base equals to the equilibrium concentration? Why we can say this? That's because the change of each is very minimal, is negligible. For example, we know the H2P minus will reach equilibrium with the HP2 minus through this, reaction, right? So the molarity of these two are relatively big, but the H plus, as we know, is 10 to the negative 6.5, which is very, very small. So there is a change. Let's say this is C1, this is C2. So at equilibrium, we will say this is C1 minus 10 to the negative 6.5. This is C2 plus 10 to the negative 6.50. This is 10 to the negative 6.50. So obviously, if C1 and C2 are not too small, which means the solution is not too diluted, we can ignore these two. And then we will say the initial molarity equals to the equilibrium molarity, right? There's no issue. But when we use the similar idea to the second part, pH equals to 13, which means this one is close to pK3. So we will say 13.00 equals to 12.32 plus logarithm, still conjugate base, P3 minus over the HP2 minus. So in this case, we should use HP2 minus, we should use P3 minus reacting with water and get HP2 minus and hydroxide. The reason why we use this way is because this solution is basic with a pOH of 1.00, right? So you can also calculate the C1 prime here, the C2 prime here, right? And but this time, the OH is 10 to the negative is 0.1 basically, right? 0.1. So this is why you cannot, ignore the C1 prime minus 0.1. You cannot ignore the C2 prime plus 0.1. Basically, the 0.1 is comparable with the C1 prime and the C2 prime. So in this case, we cannot simply accept the equilibrium molarity of these two are equal to the initial molarity. So this is why, in order to get such a large hydroxide concentration, we need to add some extra hydroxide. We cannot fully rely on, the hydrolysis of the P3 minus, because if you finish the calculation, you will realize even all of the P3 minus completely hydrolyzed, it is still not enough to produce 0.10 mole per liter hydroxide. So this is why we need to add additional amount, and then you can do some further calculation to confirm what is the amount needed. So this is the trick of the question. So I will also provide you another similar question for you to practice.